Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So, in this video we will look at this technique called batch normalization, which helps in training the network, a deep neural network better, and it is kind of can treat of it as a continuation from the data processing, pre-processing that we saw in the previous lecture. Okay. So, what is we will look at what is batch normalization, and then we will consider what is the problem here when you are training a deep neural network. So, what happens? Okay. So, when we train a deep neural networks, what happens is that the distribution of each layer's input changes during training. We will see why that is in the next slide, but we can see that as we train, because the weights keep changing, the input to a particular network, a particular layer in the network would be changing dynamically. So, because if the weights change drastically between two iterations, you have the same issue, right. And the solution is to somehow make sure that the distributions do not change too much, in the sense that the distribution of the inputs to a layer do not change too much. Okay. So, let us see how what do you mean by that and how we can address that problem. Okay. So, let us consider this slightly more like a functional form. Let us say, okay. So, F1 and F2 are some transformations. So, what is the transform that happens in a neural network in a layer? So, in a layer what happens? You have W transpose x plus B, okay, where x is the input to that layer, right. This is one transform that happens, and you pass it through a non-linearity. So, then you can get something like e raised to minus or to minus, right, can do something like that. So, that is a transformation that happens, right. So, when W changes with every iteration, you can see that the inputs to a particular layer will also dramatically change. So, you can think of F1 and F2 as the transformation that happens to your inputs at every layer. Okay. So, if you have two layers in succession, each layer characterized by theta by these parameters theta, which are nothing but the weights, and let us say another layer 2 characterized by this another set of weights theta 2, right. So, once if as theta 1 and theta 2 keep changing, you can see that so if theta 1 changes, then F1 will change. So, the input to F2 changes, right, the input to F2 will change, and if theta 2 changes, then F2 itself will change, again L will change. Okay. So, if L is an input on another layer, then L will change. In the sense the change, of course, it is expected to happen because we are trying to estimate theta 1 and theta 2, if you think of F2 and F1 as the layers in a deep neural network. But since these changes, if they are in the sense if these changes are kind of random and large sometimes, then you have problems with convergence in a deep neural network. Okay. So, what we do to address this problem in a network is to normalize each activation. Okay. So, this is before we apply the non-linearity. Typically, that is what is done, is we can do we have always use x, just to clarify the notation, we always use x to denote the input. In general, this is our training data input, that is what we usually have used x for. So, for the purposes of this video, think of x as the input to every layer. Okay. So, every layer has a set of neurons, and every neuron has a input coming into it, right. And what is that input? That input coming into every neuron is W transpose x plus B. This is the output from previous layer. Okay. So, if there are k neurons in a layer, there will be k such terms, right, k terms or k inputs. K terms or k inputs. So, this is the input that is coming into a layer, and what we do is, so I have used x pretty much for everything, abuse of notation, but then what we do is we do x minus the mean or the expectation value of x divided by the variance of x. This is what we saw earlier. This is your typical that is called normalization. But then how do we calculate expectation of x, what is this expectation of x? Okay. So, we will just go through the algorithm and then it will be very clear as to how this mean of x is calculated for every layer. Okay. So, here is the algorithm. Okay. We are considering one layer, okay. We are considering one layer. Okay. And let us say it has k neurons, okay. It has k neurons, and we are just trying to see how this batch normalizing transform can be applied to that. Okay. So, if you have k neurons, right, you have this, let us say k is 4, then we have inputs coming in from the previous layer, right. I am not going to draw it because it gets too confusing. So, multiple inputs coming in from the previous layer, and then of course, there is this W transpose x, not the affine transform that we do, okay, W transpose x plus b, right, and then followed by nonlinearity, that is the output of that particular layer, okay, that is your activation. Okay. So, then once we have that, so how do we calculate this? So, for every neuron, if you just take one neuron, let us just take one neuron. So, we have all these inputs coming to that neuron, okay, with which we can calculate the linear combination W transpose x plus b, and then following, and then you apply the nonlinearity to that, right, that is the output. Now, what do we mean by calculating the mean of x? So, this is one input, okay, to that particular neuron. So, what we do is we consider a mini batch of m training samples. So, there are m training samples in a mini batch, right, and we can, when in the forward pass, we can actually forward pass all the m samples at one in succession, okay, and we can compute this W transpose x plus b for each mini batch. So, if you have m data points, then you will have m such calculated values for each neuron. Okay. So, that is for each activation prior to passing it to the nonlinearity, you will have m such values corresponding to each data point in your mini batch. So, this mean is calculated over the mini batch. So, this is for a neuron, right. So, you have a neuron and you have m input data points. This neuron is, let us say, the first or second layer, and but then when you do the forward pass for a neuron using the weights that have already been estimated or randomly initialized, as you do the forward pass through the network, for every point in that m points in that mini batch, you will have one linear combination. Okay. So, you will have m such linear combinations, which forms with which you will estimate a mean, that is your mean, and of course, once you subtract that mean out, you can estimate the variance squared or the standard deviation square or the mini batch variance, and you will normalize every neuron with that every. So, for I equal to 1 to m over individual input training examples of that mini batch, you will calculate this normalized data point. Okay. And once you have done that, then we define two parameters gamma and beta again for every. So, this, if there are 4 of them here, there will be a gamma 1 beta 1, gamma 2 beta 2, gamma 3 beta 3 and gamma 4 beta 4. Okay. So, for every neuron they will have two hyperparameters gamma and beta, and you will do this transformation. So, how are gamma and beta estimated? They are estimated through backprop, because all this is, you can think of this as a linear layer in your network, and that is how it is typically interpreted. So, this linear layer is inserted between your affine transform, which is the linear combination of your neuron activation from the previous layer, and the nonlinearity you apply. Okay. So, it is in between these two layers you have the batch normalization layer. Okay. So, what it does is that, so this is a this is a transformation that helps to make sure that your data distribution, in the sense that the distribution of your activations of your that the activation that you compute for every neuron does not shift too drastically. Okay. They are confined to be within a certain distribution. So, when this happens, then training is automatically faster and it converges faster. So, you can think of one example where this will work is when one of the W's are too large, and it leads to, it might lead to saturation. We saw that, we talked about it earlier. So, by doing this normalization you can prevent that from happening, also by making sure you can estimate gamma and beta. Okay. So, you can also see that this is like an invertible transformation, since it cannot, you can gamma and beta can be estimated so that yi can be just equal to xi cap. Okay. That is very easy to see, I urge you to convince yourself of that. Okay. So, if the original calculated value is the one that is actually desirable, then gamma and beta can be, the network would estimate gamma and beta would to be the inverse of this transformation that we did, leading to identity. Okay. So, if this might sound cryptic, but you should read the paper, I will post the paper up there and I urge you to read it. Okay. So, just to recap once again, so for every neuron in a layer, you see that every neuron, if this is a fully connected neural network, we can think that is one we are talking about, an MLP. For every neuron in a particular layer, it gets inputs from the previous layer. Okay. We call those, we denote those inputs by x. Okay. So, and we are considering only one neuron at a time. So, for every neuron there is a linear combination of the activations from the previous layer, that is what we call W transpose x plus b. Now, for when you are doing training, there is a mini batch of data points, m data points. So, we do the forward pass and we calculate this W transpose x plus b for every data point in that mini batch, and we do a mean and variance for that mini batch for that particular neuron. Okay. And then we scale the activation of that neuron for a particular data point, input data point, by the calculated mean and standard deviation. Okay. And then of course, we multiply it by this gamma and add by beta to get a transformed variable. So, these gamma and beta are again estimated by back propagation. So, remember that if there are k neurons in a hidden layer, you will have k such parameters. So, it is an addition of k such parameters. Once you have done training, so this is how it is trained. So, for every layer you will have a gamma and beta, and it will be estimated once you are training by back propagation. Now, once you are done training, how do you do the testing and inference? So, then you still need to remember, for testing and inference you would still have to, for instance, you have to calculate this mu and sigma, right. You have the gamma and beta, but you still have to calculate the mu and sigma. So, what you do is, for that you can compute mu and sigma over the entire training set for every layer for every neuron. Okay, that is possible, and you have already converged on the appropriate values of gamma and beta for every layer and for every neuron. Okay. There are ways of computing mu and sigma as running averages, again you can do that, as well as some exponentially weighted averaging schemes are available, but this is the way to during testing you will calculate mu and sigma for every layer. This mu and sigma are for the activations for every layer, every neuron in every layer, calculate by running it through the entire forward pass data set, because that will be added computation, or you can just maintain a running average during training. So, each of these are fine. So, that is one way of doing it. And what are the advantages? So, apparently this the authors of this particular paper comment that it improves it increases learning rate. So, you can train with a high learning rate, leading to faster convergence, because sometimes you have high learning rates and you have large updates and sometimes leading to saturation. That will not happen with this, because you are doing this, you are trying to constrain your activation values to lie within a range, typically that is what you are trying to do, and that helps. Okay. It can also help you remove dropouts. So, it acts kind of like the regularization effects of dropout, advantages of dropouts apparently are also carried over by this batch normalization. Okay. Improve stability during training, same thing, because if you have sometimes your activations can be very large, sometimes your weights can become very large, leading to poor training, and that can be taken care of by this batch normalization. Okay. The extra computation burden is there, because you are adding one more layer between extra layer is added before every set of neurons. So, that is a thing, and you need to have significant batch size. So, if you use a batch size of like 1, 2 or 3, some of the large problems they require memory constraints might, if your data set is large, memory constraints might make you choose very small size data sets. Okay. And in that case, that there will be no effect, the statistical effects are lost by doing that. So, then it is no point doing that at that for those kind of problems where you have very small batch sizes. Okay. If reasonably large batch sizes, this will work very well. Okay. So, the one question that we have not addressed is the convolutional neural network. How do you do this in a convolutional neural network? Okay. It is a very interesting question. Actually, the paper addresses that. Okay. The paper talks about how to calculate it. That will be a homework question. Okay. So, now I have given you the homework already. So, for you to read the paper, I will upload the paper soon and read the paper, and inside the paper they do comment on how this particular batch normalization can be implemented in a convolutional network. Remember that what is being described in this video is how it is implemented for a fully connected neural network. Okay. So, that is all for batch normalization. So, so that is we wanted to do these two videos together, basically the data normalization as well as a batch normalization, because I think it will help you understand this better. Okay, thank you.